Hey guys, welcome to CodeChef's YouTube channel. The problem that we are going to discuss today is the minimum game. The problem appeared in Starters 12 of September 21 and has a difficulty level of easy medium. The prerequisites to solve this problem include trees, DFS and dynamic programming. The problem statement goes as follows. There is a new game Alice and Bob have invented and it has a n nodes rooted tree where the root is always node 1. Okay, and also each node, that is the ith node, has a value ai associated with it. Now the array A will be given to us and also the tree structure will be given to us. But in the diagram you can see I have already written the values associated with the ith node in red color. So the values 0, 2, 1, 4, 2, 7, 3, these will be given in the form of an array as you can see over here, but they are actually associated with the ith node in the given tree. And remember that it follows one based indexing. Now the game is as follows. They, meaning Alice and Bob, start with a marker at the root node. So let's have a marker with green color and they start at the root node and the score of 0. So the initial score of the game is 0. Now Alice and Bob move alternatively. It means that if the current turn is of Alice, the next turn will be of Bob and vice versa. Okay, and also it is given that Alice moves first. So they start with the root node and definitely who is the first person to play? First person is Alice. So let me denote that by A. In one move, they can move the pointer from a node to its one of child node and add the value associated with that child node to the score. So let's say Alice is starting over here. Okay, so what can Alice do? Alice has two options. He can go to either node 2 or he can go to node 3, and whichever node he goes to, he has to add their respective values to the current score of the game. Okay, so read this statement again clearly. In one move, they can move the pointer from node to one of its child node. So because it is a tree, you can move to the child. Okay, there can be multiple options, but you can move to only one of them. And to whichever node you move, the child's value will be added to the score of the game. Okay. So if the marker reaches the leaf node, the game ends. I mean, because it is a tree and only you can go to the child nodes in subsequent moves, sometime soon you are definitely going to reach the leaf node. So whenever the marker reaches the leaf node, the game ends over there. So this is basically the game. Now what is the motive or objective of the game? So Alice wants to minimize the score. So Alice wants to minimize the score of the game, whereas Bob wants to maximize the score. So remember how they are going to play alternate turns and the numbers will be added to the score. So Alice wants the final score of the game to be minimum, whereas Bob wants it to be maximum. Now, before they were to just start the game, Charlie arrives, he looked at the game and declared that the game was boring. So he asked them that what will be the score at the end of the game if each one of them can skip at most k moves. So the rules have changed a little. Instead of they continuously playing their moves, okay, back to back, now they are given the opportunity that each one of them can skip at most k moves. Meaning that if current move is of Alice, Alice can choose, okay, I don't want to play this move and pass on and give that turn to Bob. Okay, and vice versa. So with that, we have to now help answer the query that who is going to win the game. Okay, so what will be the, sorry, not who is going to win the game. Actually, we have to just tell the score at the end of the game because it is definite that Alice is the one who starts the game. Okay, that we know for sure. So there is only one possible score that the game can have. And remember, each of them will try to minimize and maximize accordingly. Okay, because that is their whole objective. So with this given additional condition that each of them can skip at most k moves, we have to help answer that what will be the score at the end of the game. So I think the question now is pretty clear. Let's understand the solution approach. So the solution approach goes as follows. First of all, let's solve the problem for k is equals to 0, meaning that no player is allowed to skip any move. They have to play alternate moves. So Alice and Bob have to play alternate moves with Alice starting with the root node. So let's first try to find the answer for this problem. Now, this problem can be easily solved using dynamic programming. If you are aware of trees and dynamic programming, the general idea, you can easily solve this using a bottom-up approach. What do I mean by a bottom-up approach? So I want to find the answer where Alice starts the game with the root node. But what I'll do is instead I will first find the answer for its both children. That what if the game started at this node or this node, and if I know the correct answers for both these nodes, then I can definitely find the optimal answer for the root node, because they are the children of root node, right? So this thing can be extended and extended. So in the end what you will come up with is that you have to go bottom up. That is, first of all you find the answers for the leaf nodes, okay, and then you go level by level up. That is, you travel bottom up in the tree. So this may sound very familiar to some of you, because this is exactly what happens in DFS. So we can easily perform these kind of actions with DFS. So first of all, let me denote the notation that I am going to use while explaining this example. So this example contains total 7 nodes. The values of the nodes associated are drawn in red color. So 0, 2, 1, 4, 2, 7, 3 are the values, and 1, 2, 3, 4, 5, 6, 7 are the node numbers. Okay, now I am going to draw an ordered tuple like this beside each node. Now what does that denote? It will denote that if I write 0, 0 over here, it just denotes that if the game started at this node, okay, mark my words, if the game started at this particular node, what will be the score of Alice at the end of the game, and what will be the score of Bob at the end of the game. So that is what this ordered tuple a comma b is going to denote. So now let's start processing the tree in bottom-up fashion. Okay, don't get scared by heavy words like dynamic programming. If you follow with me in the example, you will easily learn what I'm doing, and you will be easily able to implement the same in the code as well. So just don't get scared by the word DP. Okay, I'm going to simply use the words Alice and Bob in the question. So what happens if the game starts at a leaf node? It was told in the question that in each move, okay, let's say this is one node and there are many children node as well. Okay, what happens in each node? The marker is present at the current node, so the player can come either Alice or Bob, and he will move the marker to one of its children. So there are three options over here. He'll move the marker to one of the children and add the value of the child in the current score. So the current node's value is not added. The child node's value gets added in this code. Okay. So this is more than enough to let us know that definitely if the game began at the leaf node, the score of the game is going to be 0, because leaf nodes don't have any children. So easily I can just write 0, 0 over here. Okay. 0, 0, again 0, 0 for this node as well, 0, 0, and again 0, 0. What this means is that for all these leaf nodes, no matter if Alice begins the game or Bob begins the game, the score is going to be 0 in most optimal case as well. Now let's move to their parents. Okay, that is one level up. Now let's focus on this node, that is node number 2. Okay, for node number 2, what if Alice begins the game at node number 2? So if Alice begins the game at node number 2, remember Alice's objective is to minimize the score of the game. So definitely from node number 2, he will go to those children where their score plus their own value. Okay, the score if the game had begun at that particular child node plus their value is minimum possible. So what is that? For node number 4, if I can draw for node number 4, Alice has a score of 0, Bob has a score of 0. Again for node number 5, Alice has a score of 0 and Bob also has a score of 0. But if the game began at node number 2, then the marker will go to one of the child, and when it goes to one of the child, that node's value itself gets added to the game, right? So the value of the nodes are these 4 and 2 because they are written in the red color. Okay, they are given in the array initially provided to us. So here I have two options now. Okay, if I remove everything, this everything, if I just remove it, Alice has potential two options available. Let me write both of them. Okay, the two options available to Alice are either he goes to node number 4 or he goes to node number 5. If he goes to node number 4, he already knows that the answer over here for Bob, okay, because here Alice will play, then definitely here Bob will play. So we'll take the answer of Bob from here, that is 0, plus this value will be added to the game. Okay, this is one option. Another option is that Alice can choose to go to this child node, that is node number 5. In that case, again you will take Bob's value, that is 0. Okay, and the value of the node will get added as per the problem statement. So 2. Okay, so which one is favored? Can you tell which one is favored over here? So definitely Alice will choose the most minimum one. So the value chosen will be out of these two, the second one is more favorable. So we have got the value of A for this tuple. So if I just remove this everything, we have got the value over here, that is 2. Okay, how did I get this? I just checked all the Bob values for the children and added their respective node values, and out of those I took the most minimum one. So 0 plus 4 and 0 plus 2, which is the minimum 2. Okay, so I have got it over here. Now similarly for Bob, to place the value over here, we'll check all the children node, but this time we'll take Alice's value plus the node value and we'll maximize over all of them. So again 0 plus 4 and 0 plus 2, but the maximum is 4. So I take 4 over here. In this way, we have got the answer for this node as well. Now, if you calculate the answer for node number 3, again you have to check both its children, and for the first value, that is for Alice's value, if Alice begins the game at node number 3, the answer will be minimum of, check all the children, there are two children, so one is 0 plus 7 and one is 0 plus 3, which is minimum, the second one. Similarly, we can get the maximum of 0 plus 7 and 0 plus 3. So maximum is 7. So we have got the answer for these nodes as well. Now we need to find the answer for the root node. Now when you go to the root node, you only care about its children because the children already have the optimal answers. Okay. So now we have to fill two values over here. Now at this point, you can pause the video and find the answers for yourself as well and confirm with me if they are matching. So what will happen? Again, Alice will try to minimize the answer. So the two options available to Alice are either he can do a 4 plus 2. Okay, that is one option. 4 plus 2 is one option, or 7 plus 1 is one option. Which one is smaller? Definitely 6 is smaller. As for Bob, Bob will try to maximize the answer. So in that case, what are the two options available? The two options available are either 2 plus 2, okay? So 2 plus 2 is one option, or 3 plus 1. Which is bigger? Both of them are same, so it does not matter. So we have got the values for the root node as well, and that's it. We now have the values for each of the node, okay? So if I just erase this all, the final values were 6, 4. Now, once you have pre-computed this everything, we have the answer right in front of us. That is, the answer is definitely 6. Why 6? Because we already know that the game begins with the root node and Alice is supposed to start the game. So we take just take the value of Alice from the root node, that is the first value, that is 6, and we have got our answer. But this was the case where k was equal to 0, right? What if k is non-zero, that is k is greater than 0? So to be honest, the value of k really doesn't matter in this question. You might be surprised, but this is actually the case. Why? Now you can hear my argument for the same. Say you are at some particular node, okay? This is some particular node and there are some children, okay? Uh, Alice is having the current turn, okay? The marker is over here and Alice is going to play the current turn. And Alice says that, okay, I am going to skip my current move so that I get a better answer, so that the number is minimized overall, okay? Because Alice's motive is to minimize the number. So what can Bob do? So the chance will be passed to Bob. Bob can also skip his turn. So in all, the skipping of Alice did not matter, because as soon as Alice skipped, Bob also skipped. And this can go on because both of them have the same amount of skips available, that is at most k. And vice versa is also true. If Bob decides to skip at some point, Alice can also tell that, okay, you are going to skip because you want to bet, you want better chances of winning, that is the score should be maximized. So Alice will not let that happen and she will also skip. Okay, so in this manner, if one of them tries to skip, the another one will also skip and make that null and void. So the number of skips really do not matter. The only thing that matters is that you find the answer for k is equals to 0. That is, no skips are given to any of the players, and simply find the answer, and that is going to be your final answer. Just ignore the value of k uh, because it really doesn't matter in the question. So now that the idea or this whole solution is clear, let's now move to the implementation. The implementation is a clear reflection of what we just saw. Okay, we'll start from the leaf nodes, move bottom up, and at each point we'll just try to compute that for Alice the answer should be as minimum as possible, for Bob the answer should be as maximum as possible. So just keep that in mind. So the implementation goes as follows. For each test case we take the input n and k, where k is of no use. I just initialize my values, that is Alice of I. So basically Alice of I denotes that what will be the score of the game if Alice begins playing at ith node, and what will be the score of the game if Bob begins playing at ith node. Okay, initially I am just clearing them out and giving them value 0. Also the tree will be stored in an adjacency list, so I'm just clearing my adjacency list as well. Okay, ADJ is basically an adjacency list which is just a vector of vectors, a simple representation of graph. Then I take the actual input, that is the values of the nodes from 1 to n. I just do C in A of I. Similarly, I take the tree input as well, that is total n minus 1 edges are there. An edge is represented by u comma v, and I just push them back in each other's adjacency list. After that, I run my DFS from the root node, that is 1. And finally, my answer after doing all the DFS is that what will be the score of the game if Alice begins at node 1, that is the root node. Okay, so this is the main function that we have. Now let's see the DFS function where all the main part takes place. So in DFS, we have the current node u and the parent node. So parent is initially -1, default value. Then I initialize two values, max and min, which are respectively a very negative number and a very big positive number. Now I iterate over all the children of u. Okay, so if current node is u, I iterate over all its children, and if the children should definitely not be equal to parent because it's a tree. Okay, so I go to the children and apply DFS over there. Why I'm doing this kind of recursion calls? Because I want to go to the leaf nodes first and then come one level up and up and up. Okay, so bottom up I want to travel. So that is why I do these kind of recursive calls. Standard DFS stuff, if you know DFS. Then once this thing is done, once the DFS for all the children is done, It means that I have the value for the current node u, I have the value for all the children node v. So what I do, I just take the maximum of Alice of v plus a of v, because Bob is going to try to maximize. So if on current node u, if Bob is going to start, so definitely at v, Alice is going to play. So Alice of v plus a of v is to be maximized. So I maximize that over all children. Okay, and vice versa for Bob, it is going to be minimized. So Bob of v plus av is minimized. And then finally, I just update the current nodes Alice of I and Bob of I values. So how to do that? Definitely, if min is not equal to 1e15, it means that there are some children node at least. If min is still 1e15, that is a very big value, let's say infinity, it means that the current node is a leaf node. So we only want to make the updates if the current node is not a leaf node. So that's what I've written. If u is not a leaf node, make the updates as follows. Alice of u is the minimum one and Bob of u is the maximum one. And we have already calculated them over all the children in the previous for loop. So that's it. The DFS does all the part. We travel bottom up, all the values gets updated as we just saw in the solution approach. And finally, we just output the value of Alice of 1. That is, what if Alice had begun the game at root node, and that is given in the question. So that's it with the implementation. If you know DFS, it is pretty simple and standard stuff. I hope you guys understood the problem and the implementation as well. If you have any doubts, you can post them in the comments below and I'll try to answer as much as I can.